Okay, we have a last-minute volunteer camera operator today, for which I'm very thankful. Now, today we're going to run through some translations. Okay, and basically there's going to be four plus a few other, at least 4 examples. These are statements in C, and we're going to see how the Mips instruction set at level ISA 3, how the compiler translates these into the Mips instructions, set of Mips instructions. These are, the first one, score gets exam 1 plus exam 2 divided by 2 plus bonus. We'll start with that one. Then we'll do A sub 2 gets G plus B sub 3, and then G gets A sub I, and then G gets this big number, 491,521. This will be immediate addressing. But, so we're going to start with this, this first one. Score gets exam 1 plus exam 2 divided by 2 plus bonus. This is actually an example from earlier chapter. You probably don't remember it since you took the course a while ago. Okay, so now you guys remember, how do we do in PEP 9, how do we do assignment statements? How would we do this in PEP 9? The score gets exam 1 plus exam 2 divided by 2 plus bonus. What would we do? We would do what?
Load that into the accumulator.
Yeah, load this in, and then we'd add this, and then divide by 2, arithmetic shift, left or right? Right divides by 2, left multiplies by 2, right? And then and then we'd add the bonus, and then we'd store it into score. It's the same kind of thing. We have to do loads and stores, only now instead of having an accumulator, we have a bunch of different registers. All right, so let's take a look at each one of these MIPS instructions then. The first one is the MIPS load instruction. Okay, it uses base addressing with the I-type instruction. You can refer back to that table we looked at last time. Address is a 16-bit signed offset, and in assembly language, the mnemonic for load is LW, which stands for load word. So in PEP 9 assembly language, that would be LDWA or LDWX, load word accumulator or load word index register. But here you can just load word, and then you can specify an RD, the destination register. Are you with me? And do you remember how many bits it takes? How many bits is the RD field? Do you remember how many bits it is?
5.
It's 5 bits because there are how many registers? There's 32 registers, so it takes 5 bits to specify that. Okay? And so here's the RTL specification for the the destination register gets mem sub RB plus address. Okay? So that's the load instruction. And then the add instruction, we're going to have to add. So the add instruction uses, and remember, all of the computation takes place between 2 registers. Okay. So the add instruction uses register addressing with R-type instruction, and here again, here's the information that we just spoke about a minute ago. 2 to the 5th equals 32, so there's 5 bits to specify 1 register. And in assembly language, the way this works is add, you say add, destination, comma, first source, comma, second source. All right? So that's the add instruction. And now this bonus is going to be a constant. Do you remember how we did constants? Remember how you added a constant? How we added a constant in PEP 9 assembly language? Instead of saying add bonus comma direct addressing, if it were a constant, do you remember what we did? Yeah, we would equate the bonus to a value, and then how did we add it? Using what addressing mode? Do you remember? Immediate. Yeah. So it's the same. See, all these concepts all work the same. So the mnemonic, now it's interesting here that they have a different mnemonic for add immediate. So it's ADDI, A-D-D-I. And it uses, immediate is a 16-bit signed field. It's I-type instruction, and the assembly language is add immediate, ADDI, RD, the destination register, comma, RS, comma, and then the immediate field. Immediate is a 16-bit sign field, that, like we saw before. And then store, again, load is from memory to CPU, store is from CPU to memory. So store is just the same as load but flipped around. Uses base addressing with I-type instruction. Again, the address is a 16-bit signed offset, and the assembly language is SW, which stands for? Store word. And then, there's the assembly language format is SW, RT, comma, and then the address, parentheses, RB is the base register. So in this particular case, mem sub base register plus address is the destination. Okay? Is everybody clear on that? And so here we have example 12.2 in the book is, well, let's see how to translate. Score gets exam 1 plus exam 2 divided by 2 plus bonus. Now, first thing that's a little bit different is, now you remember the C memory model. Do you remember the C memory model? There's 3 kinds of variables, and where are they stored? So do you remember the first one? Global variables are stored where? Oh, good. Local variables and parameters are on the runtime stack, and dynamic allocated variables, the heap. So we're not going to be able to do the heap with Mips, but we will do globals. Okay? So now, do you remember that one of those, actually let's go back and look at the registers in figure 12.35. Notice what is register number 28? What is its symbol there? I mean, how is it notated in Mips assembly language? Register number 28 is called what? $ what? GP. Do you remember what that is?
Global pointer?
Yeah, GP is the global pointer. So that points to a fixed location in memory where all the globals are. And so you access a global value through the GP, through the global pointer. And then we also said that what the compiler does is it assigns, whenever there are variables and there are expressions that involve variables, what the compiler does is it assigns certain registers to certain variables, and then all the arithmetic operations are between registers, and it keeps track of which variable is in which register, and it only stores it when it needs to. By the way, you guys, for those of you who took programming paradigms when we did concurrency, do you remember volatile variables? Do you remember what volatile means? Yeah, volatile means it does not optimize away the loads and the stores for each individual instruction. So it translates each individual instruction without optimizing away the possible stores. But you know, the default is to have that register bank be like a cache with all the local variables, and to do them all and only do the store later when it needs to. So the default is not volatile anyway. Okay, so what we are going to assume for this example is that if we were to draw the values of the variables in the fixed location in memory, we're going to assume that score is a global variable and that it's offset 0 from $GP. And we will assume that that's going to be the compiler is going to assign that to register $S1. And exam 2 is a global offset 4, and that's in $S2, and exam 3 is global offset 8 from the global pointer in $S3. And bonus is going to be a constant value of 10. So you know, you get 10-point bonus. Instructor is giving everybody a 10-point bonus on this score. So exam 1 plus exam 2, and then 10-point bonus. And by the way, yeah, that's not 1-0 binary, that's 10 decimal. All right? So now, first of all, in order to see what the object code is, what we want to do in order to be able to see what the object code is in binary, we need to convert $S1, $S2, and $S3 to binary, the register addresses. So if we go back to figure 12.35, you see that $S1 is 17 and S2 is 18, S3 is 19, and so on. With the help of that figure, we see here in example 12.2 that $S1 is register 17 decimal. Well, that means that the register field for the S1 register is 10001, and so on. Are you with me? So you see how to calculate that? And here is the code for translating score gets exam 1 plus exam 2 divided by 2 plus bonus. So let's just do a little code walkthrough here. So check it out. So the first LW, it's load word into what? Register $S1. And now why is this? And you see the assembly language notation. 0 parentheses $GP. The 0 is the offset, and the $GP is the register that the offset is from. And so what that does, and you see that the comments begin with hashtag instead of semicolon like they do in PEP9 assembly language. And what that does is that loads exam 1 into register $S1. Is everybody clear on that? And then load word $S2 for parentheses $GP, that loads exam 2 into register S2, and that's because those are the registers that the compiler has assigned for those values. And then we add between those two registers. So we add $S3, $S1, $S2. So that register S3 gets exam 1 plus exam 2. And now SRA, what do you suppose SRA stands for? It's up there. Yeah. No big mystery, right? Shift right.
Black it out.
Right. Yeah, so shift right register, okay. And, and what do you suppose that 1 is? 1 bit, because remember the shift, there's a shift amount. And so you can say how much to shift it. Here we're just dividing by 2, so we just only need to shift it once. And then ADDI, that's add what? Immediate. So we add immediate. And notice that for the add immediate, the third argument in the assembly language statement is just 10. Right? That's the constant. You know, if you had symbols, you would equate bonus to 10, and that would be bonus, and that would be, you know, you'd have a symbol table. But, you know, to keep it simple, we'll just do that plus 10. And then store word is like this, right? And here, also up here on the slide, is the corresponding Mips machine language. And so what you should be able to do is, given the tables that have the instructions with the fields, we should be able to translate from. So this is the assembly language. And then down here in the Mips, that's the ISA3 machine language. Maybe we should do one of these. Let's see if we can decode one of these. Let's do LW. Let's do the second one. $S2 for $S2 for parentheses $GP parentheses $GP. Global pointer. So that's the second one. So that's the second row of 1s and 0s, right? Right there. Okay? So first of all, you do what? Look up the opcode for LW. So what table is that? Here it is, figure 12.39. So LW has what? So what does it say for LW? 10011. Is that right? 100. Help me out here. 10011. And then it's what? BBBBB. BBBBB. And then what? DDDDD. Is that right? DDDDD. And then what?
16 A's.
16 A's. A, da 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 da, A. 16 of them. Right? So, and what are the B's? What are those rows of B's? What instruction field? That's the base register, right? So what is our base register? What is our base register? In this particular example, what is our base register? Yeah, it's the global. And what did we say GP was? What's the address of the GP? Yeah, this is 28 decimal. Can somebody figure out what 28 is in binary? Someone verify that? 11100? Okay, so 11100. And DDDD is the what? That's the destination register, right? DDDD on this slide is the destination register. And what's the destination register in this particular example? What's the destination register? Load word into where? S2, but on this slide, in example 2, S2 is register 18, which is what? 10010. And now what is this AAAA 16As? That's what? What do you suppose that is? Yes, that's the address field, and it's the offset, it's the address that gets added to the base register. And so what is that here? That's the 4. So what is 4? How many of these are there? There's 16 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. But it's 4, right? So it's 1, 2. So this is a 1. Is that right? Well, let's see if that's what it is. Is that this? I hope so, or I'm going to have to rewind this whole thing and do it all over again. Did we get it? Does everybody see how we got that? All right, and similarly for the others, you can work through, you can see how. So, it's just like PEP9. I mean, you've got the assembly language, you got opcodes, you got the operand specifier fields, you got these different fields, and they all occupy different places, but it's all the same thing. Okay, so that's how this one gets translated. Now here's an example with arrays. And here again, the concept is exactly the same way that we did arrays in PEP9. Okay, you have to, do you remember how in PEP9, what did you have to do? Suppose we had an array of integers in PEP9. Do you remember what we had to do? We had to load the index, put the value into the index register, put the index in the index register, and then do you remember what we had to do? If it's like an array of integers and each integer is 2 bytes, you put the value into the index register, and then what did we have to do? Yeah, you have to do an arithmetic shift left to multiply it by 2, and then because there's 2 bytes per cell. Yeah, remember that? Okay. In a 32-bit computer, integers are like 4 bytes. So instead of multiplying the index by 2, you got to multiply the index by 4. So anyway, so that's the setup for Mips arrays. So to access an element of a Mips array, we use base addressing with itype instruction. And what happens is the compiler associates a $S register with an array variable, and that's the address of the first element of the array. Now here's the thing. Well, you'll see. We'll see. So, this is like programming in microcode. We don't have all these complicated addressing modes, so we have to calculate the address ourselves at the ISA 3 level. So let's see how to translate A sub 2 gets G plus B sub 3. So A is a global array. We'll assume this time that it's already loaded into $S1. G is a global value, we'll assume it's already loaded into S2. And B is a global array, and that's already loaded into S3. So now when we say the array is loaded, what do we mean? We mean the address of the first byte of the array. So how are we going to do A sub 2 gets G plus B sub 3 in Mips? Okay, so so we need we are going to need a temporary register. So $T0 is register 8. And there's the binary value, 01000. $S2 is register 17. Let's just assume that's what, well, as before, that the compiler has made these associations between the variables and the registers, S1, S2, and S3. And these are the binary values of the registers. And now let's see how the compiler translates A sub 2 gets G plus B sub 3. So look, it's 3 Mips assembly language instructions. It's load word into where? T0, okay. And what's it loading into T0? $S3, but now why is this 12? Does anybody know why that's 12? Because what are we it's getting B sub 3. Now why is it 12? Because it's 3 times 4. That's the word offset. So the compiler, when there's a constant there, the compiler knows that it's 4 bytes per cell. And so it actually generates the 12 as a constant offset. Yes, the S3 is the address of the first cell, of the first byte of the array in memory. And then we add $S2 plus register T0 and put the result in register T0. So that's how we add G to B sub 3. And then we store word from T0, and why is that 8 $S1? Well, if the 12 was because B sub 3, the 8 is because of what? A sub 2, and 2 times 4 is 8, because that's the offset. And there's the Mips machine language, corresponding Mips machine language. Are we good? Does everybody see how these examples work? Now, it's a little bit more complicated. The next one we're going to do is G gets A sub I. That's going to be a little bit more complicated here because this is not a constant now. This is a variable. If it's a constant, then the Mips compiler can just multiply this by 12 and put the constant offset there. But if it's a variable, then that's more complicated. Now we're going to have to do the arithmetic shift. Now we're going to have to do an arithmetic shift left, depending on what this value of I is. So the Mips shift left logical instruction is going to help us do that, and that's SLL. So it uses register addressing with R-type instruction, and we have this SHAMT, which stands for shift amount. It's a 5-bit shift amount field. And there's the assembly language format. An example of just the plain old ordinary shift left logical instruction is this SLL $T2 $S0, comma 7. That will actually shift left 7 bits. Isn't that slick? I can do that all in just one cycle. Just one cycle. So the hardware is designed to be able to do that. It's called, by the way, that, we didn't have time to, it was beyond the scope of the course to do that, but the hardware unit that does that is called a barrel shifter. I have an interesting paper if you want to read about barrel shifters. Oh, by the way, speaking of papers, let me just interject this that has nothing to do with the topic at hand. I mentioned the other day that the thing about the Mips architecture is that it was the basis of a open source hardware initiative. It's actually not Mips. Mips is actually a predecessor. It's the same people who designed Mips designed this open source thing, but it's very, very similar. But it is, the instruction set is a little bit different. It's a different instruction set. And in fact, if you're interested in that, it's called, it's pronounced RISC-V. And I have a paper online actually, and also I have a link to the homepage. And I think if you read that paper, and if you are interested in it, you'll see, and if you read up on it, you'll see that it's very much like Mips. It's the same. They have the same kinds of instruction formats and instruction types, and a lot of it's very, very similar. But it's not exactly the same. I might have left the wrong impression last time. Okay, so getting back to shift left, this example, shift left 7, notice that 7 in binary is 0, 0, 1, 1, 1. And here in the Mips machine language, this is the shift amount field right here, 0, 0, 1, 1, 1. So that tells you that. And then the 1, 0, 0, 0, that's the 16, so that's this third field right here. And the 0, 1, 0, 1, 0, that is the address of the $T2 register. So that's an example of how the shift left instruction works. And the main thing that we have to do, that we have to realize whenever we translate this program, this statement, this C statement, is that a 32-bit MIPS word is 4 bytes, which means the index must be multiplied by 4, which means we have to shift 2 bits to the left. So here's an example of, here's how the compiler would translate G gets A sub I. And here again, we will, and when I give you these exercises, and by the way, you guys, you'll have all that documentation, that same packet of information, you'll have that on the final, and there's an exercise to do these hand translations, and you need to know how to do them. And, you know, just, here's an example of translating with a real commercial industrial strength machine instead of our PEP9 virtual machine. So, so here's the translation of G gets A sub I. So I is a global variable. We will assume it's already loaded in register $S0. A is a global array already loaded in $S1. And G is a global, and that is in $S2. So now do you see how that first instruction works? Shift left logical. What is it shifting left? What is in S sub 0? And we assume that's where the I is. Are you with me? So that multiplies the I times 4, and it puts the value in a temporary register $T0. Are we good? And then we add the content of register $T0 with the content of register $S1. And why are we doing this? What are we adding here? The address of the first array with the what? With the displacement. See, we don't have an addressing mode to do this for us automatically. We have, at the ISA 3 level, we have to calculate the address ourselves. We have to have a separate, so we don't have, there's no indexed addressing. There can't be, because indexed addressing requires an arithmetic computation, and that takes cycles. Do you see what I mean? So this is the kind of thing that we would do in, this is the kind of thing that we do in the MIC2 level for PEP9, but in MIPS, it's at the ISA 3 level. That's the difference between CISC and RISC. So what was in microcode is in ISA 3 level, because there's no microcode. And then load word actually takes S2 gets A sub I. And why do we have that 0 here? Over here? Why do we have this 0 here? Whereas we had 12 in one case and we had 8 in the other case. Why do we have 0 there? Because we have calculated the offset. Do you see? So we add 0 to that, to our calculated offset. We have calculated the offset dynamically according to the value of I. So that's G gets A sub I. One more in between these two. There's one more thing we want to look at here. As in PEP9, there is the runtime stack. You know, we have a runtime stack in MIPS. And remember, in PEP9 we have a special instruction called add SP and another one called sub SP. Remember how we did that? And how did we allocate storage on the runtime stack? Remember what we did? You have to make the stack pointer here. If this is a stack, you have to make the stack pointer go up. Yeah. Yeah, well, it depends on how much you push. Yeah, so you would sub SP to allocate and add SP to deallocate. Well, they don't have special, I mean, the stack pointer is just one of the one of the registers in the register bank. So you just use add immediate. That's how you, and so here's an example of how you see it's add immediate, and you take, and what do you add? You take $SP and then a -4. So you're adding what's in the stack pointer to -4, and you're putting the result in the where? Back into the stack pointer. Do you see? So it's just an add immediate. I mean, there's no special stack instruction because the stack, you can add immediate to any one of those registers. Well, except for the 0 register, that's read-only. Is everybody clear on that, on how that works? So there's allocating 4 bytes of storage on the runtime stack. Now, here is a really interesting a really interesting situation that is directly because of our RISC design philosophy. Look, you guys, suppose G is a variable and we just want to do G gets 491,521. Now, let's think about this for a minute. How big are the registers in this Mips machine that we're looking at? How many bits? There are 32 bits, which is 4 bytes. Now, what is the numero uno, the number one design objective of RISC? It's that what? Do you remember what? I think there were like, each ISA3 instruction, except for load and store, executes in what? One cycle. What does that mean? And what, as a result of that, it's one cycle. That means we can't have variable length instructions, right? So each one executes in one cycle. So the control section has no microcode. So what does that mean? Every ISA3 instruction has to have the what? The same length. But look, so how are we going to have immediate? How are we going to be able to add a 32-bit immediate? Because part of that, because with immediate addressing, where's the immediate field? It's in the what? It's in the instruction. But part of that instruction has to be the what? The opcode. So look, so here's the question. The immediate field is just 16 bits, but the registers are 32 bits. So how do you I say add a 32-bit constant. How do you like load a 32-bit constant? Or add or load, whatever. Okay? You see the problem? The problem is this 491,521 is longer than 16 bits. But the immediate field is only 16 bits wide. So here again, this is in PEP 9, how did we add two 16-bit integers? Because our data paths were only what? Only 8 bits. So we had to do it what? Well, we had to do it in least significant byte first, and then save the carry, and then the most significant byte. So it's the same, but that was at the microcode level. But here, it's the same kind of thing. There is no microcode. So at the ISA3 level, we have to do this what? We have to do it in 2 cycles. With 2 instructions, literally with 2 instructions. 2 ISA3. And those 2 instructions are LUI, which stands for load upper immediate, and OR-I, which stands for OR immediate. And that's how we're going to do this, and that's how we're going to translate this instruction. So here's the translation of the instruction. So check it out. Let's assume that G is a global variable, and that is stored in $S2. Now, I don't want to go through all the rigmarole, but if you had to, you could translate 491,521 in decimal into binary, could you not? Do you remember how to do that? Successively divide by 2. Or you could probably find some calculator on Google that would, or maybe you have a binary. Do you guys have a binary mode on your calculators? If you work it out, it turns out in hex to be 0007 and then 8001. So the way this statement is translated, G gets 491,521. It's load upper immediate 0007 into register S2. So we are assuming that G, the global variable, has been assigned register S2 by the compiler. And so what that load upper immediate does is that sets the most significant byte to 0007, and it zeroes out the lower byte. And then we OR immediate $S2 with 0x8001. And so if you have to do that in 2 parts. So here again, this has the flavor of microcode because there is no microcode. You see what I mean? PEP 8 really, or PEP 9 rather, was really designed along the historical lines of the way computers evolved. Because computers evolved, the instruction sets and the addressing modes of the computers evolved to make it easy to translate from HOL6 language like C to assembly language. And so all these complex addressing modes are there as a help for us to be able to make those translations easy. But what happens is, behind the scenes, you've got all this microcode that has to do all of this implementation of these complex addressing modes. On the other hand, in a RISC machine, when we don't have in a RISC machine, when we don't have these complex addressing modes, that means that computation has to be done at the ISA3 level. So the compiler has to generate the code to do what is normally done in the microcode of a CoSc machine. Yeah, question? Well, that's a good question, and that goes back to the performance equation, and the answer is it's debatable which is faster. There is a resurgence now of CoSc people, of CoSc projects, and because basically what you can do in hardware is you can usually do in hardware a computation faster than you can do the equivalent computation in software. So the argument is the more that you can do in hardware, the faster the execution. But you know, it's complicated, and it's not clear cut, because those two. Here, let's go back and look at let's review the performance equation. Here's the system performance equation in figure 12.33. So what happens is, with a CoSc machine, you minimize the time per program by minimizing the number of instructions per program. That means that all that microcode happens in hardware, you see. But with a CoSc machine, what does that do? That causes the number of cycles per instruction to increase. So the question is, well, if you decrease this but you increase this, what's the net effect? Well, it depends on how much this decreases by how much the other one increases. Are you with me? And on the other way around, conversely, the other way around, with a RISC machine, you minimize the number of cycles per instruction, and you minimize it all the way down to 1. But that means that you have more instructions per program. And we just saw that you have to do in 2 instructions what you could do with 1 in PEP9. So it's debatable which one is, you know, and because it's not clear, you know, because there's a trade-off. You minimize this, you maximize this. And and furthermore, it's also complicated by other questions like power efficiency, you know. So one of the things that we have found is that for mobile devices, this ARM RISC machine is much more power efficient than what Intel was able to get with. They tried very mightily to get the x86 architecture to be viable for mobile devices where power efficiency is really crucial, because you have battery life that you have to worry about. These mobile devices aren't plugged in as we carry them around. Right? So it's not clear. And in fact, I have one of the papers on one of the resources online on our website is a recent paper about some people who are arguing for a comeback for CoSc. You might be interested in reading that. Anyway, so it's all hotly contested. I will say one thing though. I hesitate to put this online, but I will anyway. I'm going to be a little pundit here and hazard a guess. I have seen in the past when people, do you remember in programming paradigms when we learned Scheme, which is a dialect of Lisp? There was a company once that said, wow, if we can do in hardware things a lot faster than what we can do equivalently in software, then maybe what we should do is build a Lisp machine. The company was called Symbolics, and they had the Lisp interpreter in hardware, and they were convinced that was going to be fast. And for a while, the company was good, but was viable, but it eventually went out of business. There was also a move. You guys have programmed with Java, right? You know the Java virtual machine? Well, people have made Java chips. They put the virtual machine in hardware, and they say, look, we're going to plug this into the circuit board, and people were convinced that, some people were convinced that we were going to have Java hardware. Well, it's kind of like the same thing, you know. The thing about, and now this argument with software, the software-hardware interface, people are looking at modern compilers like, have you heard of Llvm? That's the CLang, you know, the CLang toolkit is the one that Apple uses, and they developed this Llvm. Somebody know what Llvm stands for? Can you Google that real quick?
Low-level virtual machine.
Yes. Yeah, so if you Google LLVM, you'll see that it stands for low-level virtual machine. So some people are saying, aha, here we have this low-level virtual machine. Let's put that in hardware. And if we do are you with me? So we'll put that in and have that be our microcode. You see? But I don't know. I don't think it's going to work. That's my prediction, is things like that aren't going to work. Because the problem is that they are too specialized, and then if you find bugs in them, they are difficult to correct in the hardware. Whereas in a software system, all you have to do is release an update. So it's kind of like you need the lowest common denominator only in the hardware. And that's kind of like, it's not exactly related to the RISC versus CISC thing, but it is related. Not precisely, but it's the same kind of idea. All right? Good deal. So see you next time.